If you want to build a skyscraper, you use iron.
Right.
And if you want to build the smartphone that's sitting in your pocket right now, you rely on silicon. We we really tend to obsess over these main characters of the periodic table.
Oh, for sure. The heavy hitters.
Exactly. The heavy hitters that take center stage in the story of human progress. But what if you want to, I don't know, shave a few critical pounds off a spacecraft so it can actually break orbit?
Yeah. Iron and silicon are definitely not going to help you there.
No, not at all. You need something entirely different. You need an element that was forged in a dying star, scattered like invisible dust across the Earth, and surprisingly, completely ignored by biological life for billions of years.
It's just such a wild resume for a metal.
It really is. So today, we're taking a deep dive into the shadows of the periodic table to look at element 21, which is scandium.
And it really is the ultimate, the quiet overachiever of material science. Like, if you haven't heard of it, you aren't alone. It doesn't build empires loudly, But when you look closely at the source documents we're unpacking today, you realize it's quietly optimizing the absolute highest tiers of the modern world.
Okay, so let's unpack this. Because our mission today isn't just to give you a dry chemistry lesson. We are exploring the entire concept of hidden potential.
Yeah.
We're looking at a material that proves you don't actually need to be the most dominant force in a system to radically change how that system performs.
Which is such an important takeaway.
Totally. By the end of this deep dive, you're going to see how the smallest, the most overlooked things can create massive leverage, a concept that applies to engineering, sure, but also just to how we think about progress in general.
Yeah, the philosophical implications are actually huge.
So let's just get into it. What exactly is element 21? Like, what is the actual physical identity of scandium?
Well, to understand its identity, you kind of have to look at a massive physical contradiction. So scandium sits at atomic number 21 on the table, making it a transition metal. And if I were to just hand you a pure chunk of it, it would look like a solid silvery white metal.
Pretty standard.
Yeah, fairly standard. Over time, as it oxidizes in the air, it can develop this faint yellowish or even a pinkish tint. But the real surprise is what happens when you weigh it and then try to melt it.
Right, because usually with metals, there's a trade-off between being lightweight and being durable.
Yep.
Like, aluminum is incredibly light. But
You can melt an aluminum can in a campfire.
Exactly. It doesn't take much heat at all.
Right. But scandium's density is just 2.99 grams per cubic centimeter. To put that in perspective for you, it sits right on the border between your typical featherweight metals like aluminum and your much heavier high-strength transition metals like titanium.
Wow, okay.
So it's incredibly light. But despite that lack of density, it holds its ground against punishing heat. I mean, its melting point is 1,541 degrees Celsius.
That is absurd for something that light.
It is. It doesn't even boil until it hits nearly 2,900 degrees.
It's like it breaks the rules.
Yeah.
It's a featherweight that can take a heavyweight punch.
Exactly.
And when you look at its cosmic origins, that ruggedness actually starts to make sense. Because this element wasn't born in the Big Bang along with, hydrogen and helium.
No, not at all.
It took dying, exploding stars, literally supernovas, to generate the extreme energy required to forge element 21.
Which perfectly explains its geological footprint on Earth, actually, and why it is so incredibly frustrating for humans to get our hands on.
Because it's everywhere but nowhere.
Basically, yeah. Because it was forged in these late-stage stellar explosions, it was just scattered into planetary materials as the solar system formed.
Yeah, I see.
So cosmically speaking, it's rare, but on Earth, it actually exists quite widely. It just doesn't exist in concentrations.
Right. It's wide but incredibly thin. My instinct, looking at the distribution data in the sources, is to compare it to like someone taking a handful of powdered sugar and just blowing it across an entire beach.
That is a brilliant analogy.
Thanks. Because it's technically everywhere on that beach. It shows up in trace amounts, in obscure minerals like thornveitite or mixed into bauxite. But good luck scraping enough together to actually bake a cake.
Yeah, good luck is right.
Which means mining it directly has to be an absolute economic nightmare. Like, you'd spend way more energy moving mountains of dirt than the microscopic bits of metal are actually worth.
You've hit the nail on the head. What's fascinating here is that scandium's defining geological trait is not absolute scarcity, it is dispersion.
Dispersion. Okay.
Yeah, it isn't like gold or copper. You can't just go out, find a rich vein of scandium in the rock somewhere and open a mine.
Right, there's no scandium rush.
Exactly. Because of this extreme dispersion, it has a very specific supply chain identity. It is almost exclusively a byproduct. You only get it by accident when you are processing massive amounts of other ores, like titanium or rare earth metals.
Okay, so if it's this, like geological ghost, and gathering it is this difficult, the payoff has to be astronomical.
Oh, it really is.
Because engineers and material scientists wouldn't go out of their way to meticulously filter this powdered sugar out of the sand unless it was doing something basically magical at the atomic level.
Right.
So what exactly is its chemical superpower?
Well, its superpower is acting as a chemical bridge. So scandium desperately wants to give away 3 electrons. It's what chemists call a +3 oxidation state.
Okay, so it's highly reactive in that way.
Highly reactive. Because of this, it bonds incredibly aggressively with oxygen and the halogen family, like chlorine and fluorine.
Which I imagine makes it hard to work with.
Oh, yeah. It makes it stubbornly difficult to purify into a pure metal. But it also means it interacts with other metals in highly stable ways. And its true modern fame comes down to exactly one partnership.
What it does when you mix it with aluminum.
Exactly.
Now, here's where I want to push back a bit. Because if you're listening to this and you know a bit about aerospace or engineering, you might be thinking, wait, aluminum is already great.
Right, it's everywhere.
It's light. We use it for airplanes all the time. And if we need something stronger and more heat resistant, we just use titanium. So why bother with scandium at all? Is it really that important if it just, piggybacks on aluminum?
That is the perfect question. And it all comes down to workability and weight. So titanium is incredibly strong and handles heat beautifully, but it is heavy.
Right.
And it is notoriously difficult to machine and very hard to weld. Aluminum, on the other hand, is wonderfully light and easy to shape. But on its own, its atomic structure is prone to failure under extreme stress.
It just can't handle the heat.
Exactly. It isn't strong enough for the absolute highest tiers of aerospace environments without getting way too bulky.
So we need something that has the lightness and workability of aluminum, but the heat resistance and strength of titanium.
And this is where scandium steps in. The data in our sources shows that if you take a standard aluminum alloy and add a microscopic amount of scandium...
We're talking really tiny amounts, right?
Whoa, incredibly tiny, sometimes less than 0.5%. Yeah, and just that tiny fraction completely transforms the properties of that aluminum. It makes it dramatically stronger, it makes it weldable, and it skyrockets its heat resistance.
And we should definitely explain exactly how that happens, because the science here is brilliant. It's a process called grain refinement.
Yes.
So when you mix that tiny fraction of scandium into molten aluminum as it cools, the scandium atoms bond with the aluminum to form these incredibly stable microscopic crystals.
Right. And to visualize why that matters, imagine the atomic structure of regular aluminum.
Okay, so if I'm picturing it, it's a bit like a stack of sliding plates, right? When the metal is put under stress, those atomic layers just want to slip and slide past each other.
Precisely. Which is why the metal bends or breaks.
Right.
Now imagine taking those sliding plates and driving microscopic steel pins straight down through them.
Oh, wow. Okay.
That is exactly what those scandium aluminum crystals do. They pin the grain structure of the metal in place. They act like rebar in concrete.
That is such a good image. So the scandium isn't actually doing the heavy lifting itself. I mean, there's barely any of it in there.
Exactly. It's just locking everything else in place. It stops the aluminum's atomic layers from sliding when the metal is stressed or heated.
That completely reframes how I think about alloys. Like, it takes a common, everyday metal and just turns it into a superhero.
It really does.
Which is why it's used in elite, highly specialized applications.
Yeah.
We're talking aerospace components, spacecraft frames, 3D printed metal parts where precision is everything.
Yeah, and you even see it in high-performance sports equipment like professional baseball bats and bicycle frames. It pushes things to the absolute limit of physics. It really operates as the specialist coach of material science.
I like that, the specialist coach.
Yeah, think of a professional sports team. You have your star athletes, the ones scoring all the points. That's your aluminum, your carbon, your iron.
Right.
But then you bring in a highly specialized coach who tweaks the team's biomechanics, adjusts their diet, refines their sleep schedules.
But the coach doesn't actually score a single point.
Right. But suddenly, because of those microscopic adjustments to the system, the star players are performing 10–20% better.
Wow.
Scandium's value lies entirely in how it changes the performance of the whole system at the margins. It represents the transition from good enough to ultimate optimization. When you are building a fighter jet, good enough just doesn't cut it.
No,
Yeah.
absolutely not. You need the absolute maximum strength with the absolute minimum weight. It's
Exactly.
the ultimate quiet modifier.
Oh.
And yet there's this massive glaring paradox when we look at the broader picture of element 21.
Oh, the biological side of things.
Yes, because human engineers are completely obsessed with it. We will sift through literal tons of rock to extract a handful of this stuff just to make a spacecraft lighter.
Hmm.
But biological nature, over billions of years of evolution, life on Earth looked at scandium and completely ignored it.
It is a profound biological void. There is absolutely no known essential biological role for scandium.
None at all.
None. No DNA, no proteins, no bones, no microbes, no plant life relies on it. To biology, its identity is simply absence. Oh, and it's generally of low to moderate toxicity, so it's not even a major threat. It's just not there.
Which really raises the question, why? Why did nature completely bypass an element that we humans find so structurally useful?
Well, if we look at the chemistry, it makes perfect sense. Biology is fundamentally a water-based game.
Right. We're all mostly water.
Exactly. Life evolved in the oceans, and our cells run on aqueous solutions. For biology to use an element, it generally needs to dissolve well in water so it can be transported through roots or bloodstreams or cell membranes.
And I'm guessing scandium doesn't play nice with water.
It really doesn't. Remember that +3 oxidation state we talked about?
Yeah, the aggressive bonding.
Right. Scandium ions are highly charged and relatively small. When they hit water, they tend to react and form solid hydroxides. Basically, they precipitate out as a solid almost immediately.
Oh, so they just drop out of the solution?
Exactly. They are incredibly insoluble. So from an evolutionary standpoint, early life couldn't absorb it easily. And because evolution is inherently practical, it just bypassed it entirely. Nature builds with what is abundant and biologically accessible: carbon, calcium, oxygen.
That makes a lot of sense.
Yeah.
Biology doesn't need to build an aerospace-grade skeletal system to survive. It just needs good enough to reproduce.
Right.
But human ambition operates on a completely different frequency. We aren't satisfied with good enough. We want to defy gravity. We want to travel to other planets. We want fuel cells that generate power with unprecedented efficiency.
And if we connect the bigger picture, the divergence between biology and human engineering tells us exactly what era of civilization we are entering.
How so?
Well, scandium represents the era of absolute efficiency. We are pushing past the limits that nature accepted. The aesthetic of this element is clean engineering. It's cool, technical, subtle.
See what you mean. I mean, civilization would absolutely survive without it. We sit at like a dependency tier 3 or 4 with this stuff. We wouldn't go extinct if scandium disappeared tomorrow. But the elite materials, the very technologies that push our boundaries, those would vanish.
I really love that perspective. It's basically the physical embodiment of human ambition. But as we dig into the extraction methods outlined in the sources, that ambition comes with a serious reality check.
Oh, a massive reality check.
Because we have established that we desperately need this incredibly dispersed metal to build our high-efficiency future. Like, lighter planes mean drastically less jet fuel burned. Scandium-stabilized zirconia makes solid oxide fuel cells incredibly efficient, which is huge for clean energy.
Right.
But how do we actually get our hands on it without tearing up the planet in the process?
This raises what is arguably the most important question for the future of specialized materials. Because the main obstacle for scandium isn't demand, it's availability and the cost of processing.
Because it's so dispersed. Exactly. Because it is a dispersed byproduct, producing it is inextricably tied to massive industrial operations. Historically, that means digging huge mines, creating vast amounts of chemical processing waste, and using tremendous amounts of energy just to refine out those trace amounts.
And here's the dilemma that really stands out to me. Aren't we just trading one massive environmental problem for another?
How do you mean?
Well, we are trying to build this optimized green future, right?
Right.
Planes that burn less fuel, highly efficient power grids. But to get the scandium to do it, we have to process thousands of tons of toxic sludge. It just feels incredibly counterproductive.
It is a major paradox, and there's also the risk of geopolitical supply concentration, where only a few places control the market. But environmentally, if the demand for scandium skyrockets to build these clean technologies, the absolute worst-case scenario would be opening up thousands of massive low-yield mines that strip the Earth simply to chase microscopic trace elements.
Yeah, you'd generate far more ecological damage than you'd ever save in jet fuel. So what do? Do we just hit a wall? Do we abandon the idea of ultra-efficient alloys because the extraction cost is just too high?
Not at all. The path forward forces us to completely reframe our relationship with industrial waste. The source material actually proposes a really elegant solution.
Okay.
The most viable future for scandium isn't in digging new holes. It's in clever chemistry. We already have mountains of what's called bauxite residue. It's often known as red mud.
Red mud, right, I've heard of that.
Yeah, it's a highly toxic byproduct left over from refining aluminum. We also have vast amounts of waste from titanium processing. The scandium we need is already sitting in those waste piles. We've already done the digging.
Wait, really? So the solution is basically treating our old industrial garbage dumps as the mines of the future?
Exactly. And the technology to do this is fascinating. Instead of brute force mining, material scientists are developing advanced techniques like solvent extraction and highly specific ion exchange resins.
Okay, ion exchange resin sounds incredibly dense. How does that actually work?
Think of it like a highly specific chemical magnet or a microscopic filter. You take that chemical sludge, treat it, and run it over these specialized resins.
Okay.
The resin is programmed to ignore the iron, ignore the silicon, ignore the aluminum. But when a scandium ion floats by, it chemically grabs it.
Oh, wow.
Yeah, you essentially wash the sludge, and the resin selectively plucks the powdered sugar right out of the sand.
That is brilliant. So instead of just viewing this red mud as a toxic liability that we have to babysit for the rest of eternity, we start viewing it as an asset.
Exactly.
We go back into the waste streams of the 20th century, we extract the scandium to build the clean energy of the 21st century,
Yeah.
and in the process, we actually clean up and neutralize the toxicity of that red mud. We're solving two massive problems at the exact same time.
It is the ultimate closed-loop ambition. It forces us to realize that as our technology gets more advanced, our definition of what constitutes a resource has to evolve.
That's a great way to put it.
A century ago, bauxite residue was just dangerous trash. Today, it is a crucial reservoir for the metals that will literally build our spacecraft.
It brings the entire story of Element 21 full circle. It is the absolute definition of hidden leverage.
It truly is. So what stands out to you the most when you look at scandium's entire profile?
For me, it's the philosophy of the quiet modifier. We started by looking at a metal that barely anyone knows about. It's incredibly light, it's rare, and it's scattered like dust across the globe.
Right.
Biology literally couldn't find a single use for it because it dissolves poorly in water. But when human engineers introduce just a tiny fraction of it into an aluminum alloy, it pins the atomic structure together and radically transforms the performance of everything it touches.
Yeah.
It doesn't demand the spotlight. It doesn't need to be the main character. It just makes the entire system fundamentally stronger.
It really proves that in complex systems, value isn't always about volume or brute force. Sometimes the most critical component is the one providing precision at the margins.
I think that's such a great takeaway for you listening right now. Whether you are managing a team, building a business, or just analyzing your own daily habits, you don't have to be the loudest or most dominant force in a system to fundamentally improve how that system performs.
Oh, definitely.
You don't have to be the iron or the silicon. Sometimes the greatest leverage comes from the smallest, most precise adjustments. Finding your own internal scandium, so to speak.
That is a really powerful way to look at it. And as we wrap up this deep dive into the sources, I want to leave you with one final thought to mull over, building on that paradox of extraction and waste we just discussed.
Well, I like where this is going.
So we know that humanity's technological future relies increasingly on these specialized materials. Elements like scandium that are incredibly powerful but dispersed in literal dust across the Earth. So, how might this shift the entire global balance of power over the next century? Will the future belong not to the nations that possess the biggest, most destructive minds, but to the nations that develop the most brilliant chemical algorithms to harvest the microscopic dust we currently just throw away?
That is wild to think about. A total geopolitical shift based on who has the best chemical magnets.
Exactly.
Well, something to think about the next time you step onto a plane or look at a pile of scrap metal. Until next time, keep diving deep.